So we are in week 11. So welcome to the 11th problem solving session of parameterized algorithms. So what we are going to discuss today is called matroids. So let me define matroid for you. So it's a combinatorial structure. So it is defined in a combinatorial way, but its inspiration is from graph theory and linear algebra. So in fact, it connects these two areas of graph theory and linear algebra. And we have seen in the videos that how Matroid helps us in designing fixed parameter tractable algorithms. The questions that we are going to discuss today are going to be focusing on matroids only, so it is important that we define what is a matroid formally. So matroid is a tuple u comma f. So it's mathcal f, that is curly f, where u is called the universe and f is called, it's a family of sets over the universe. So it's this two tuple u comma curly f, and it satisfies the matroid axioms. There are three matroid axioms that this set system should satisfy. Okay. So what is the first axiom? That the empty set should be in the family curly f. The second axiom is that if A is in the family and B is a subset of A, then B is also in the family. Okay, so this in short, so for our convenience, this axiom, this property will be called the hereditary property. Okay. So there's a third axiom, which says if A is in the family and B is also in the family, but the cardinality of A is strictly smaller than the cardinality of B, then there exists an element B in B alone, such that if you merge A with this element, then that union will be in the family. So for convenience, we will call this property as the exchange property. So this is a definition of matroid. So I hope that the definition is clear.
Yes, except last point, because last point is so very obvious, because since B is a part of the family and the cardinality of B is greater than A, so clearly B includes what? B includes, okay, so B includes everything, whatever is there in A, and plus something extra. And so if I take the union of A with that something extra, so that will clearly be the part of the family.
No, so are you assuming that A is a subset of B?
Yes, probably. But here, I mean, A and B could be different, I think.
Yes. So the universe is a set of elements, and you have taken some of these elements and call it A. You have taken some of the elements and call it B, and A and B need not have any elements in common. So what it is saying that, okay, if B is larger than A, then there is at least one element in B which you can include with A, then that larger set is also going to be part of the family.
So Yeah. So since A and B are disjoint here, so the entire set B,
Yes.
uh, yeah. So entire set B can be included with the set A because all the elements of the set B in this case won't be there in the set A. So can we include all the elements of the set B with the set A, and will that still result uh, as a into a family member?
That depends on the way the particular matroid is defined. But for a set system to be called a matroid, these three axioms should be satisfied. Now, how A and B? So you are saying that okay, if there is a matroid, so this is a definition of a matroid. Now you are saying that okay, if there is a set system which is a matroid, which is known to be a matroid, and A and B are two disjoint sets which belong to the family F, then is A union B also belonging to F? That is the question you are asking.
Yes, yes. I mean, something like closer property kind of thing.
I'm not. I'm not. Uh, Let me give it a thought. I don't think that is going to be true. So A is separately part of the family, B is separately part of the family, and A and B have no intersection. So that A intersection B is phi. I'm not convinced that A union B must be part of the family. That kind of thing may not happen. So I think we'll be able to answer this question once we progress in this session and look
Yeah,
at some
yeah, sure.
examples.
Yes, yes, yes.
So for now, we have defined what is a matroid, that on what grounds we are going to call a set system a matroid. Okay. So now we can look at maybe the first question. I think, yeah, first question we can look at with the definition only. So let's take the first question. So you read the question.
Okay, so does this mean that capital E here is the set of the universe? Is the U?
Yes, the
Okay,
first in the tuple, the first thing is the universe, and the second thing is the family.
okay.
Right. So we have been given a universe and the family I, which are nothing but some subsets of the universe. So you have to decide that okay, for this definition is E comma I, the tuple E comma I is a matroid.
Yes, but I mean, so if I use the heredity property here, then I can say that if heredity property says that if A is the part of the family, and if B is a subset of A, then B would also be the part of the family, is it? Even though the heredity property is not visible to me, if you scroll it up a little bit, then yeah, thanks. So yes, so
Yes.
then B will also become the part of the family. But then where is the set A here? And I can only say that phi is the part of the family. How can I say that one is a part of the family? Okay, so if I mean these are given to us, like say 1, 2, 3, and then 4. If these are given to us as a family, then clearly this 1, 2, 1, 3, 1, 2, 3, 4 use heredity property is being followed here. heredity property is being followed here. And what about the exchange property? So in the exchange property, say if I take, yeah, so exchange property is also being followed here. Wherever I find, say that the cardinality of B is greater than A, like say if I take 1 and then 3, 4. So 3, 4, so this all the elements small b, which are the elements of B minus A. So 3, 4 is are those elements. So therefore 1, 3, 4 should also belong to the family. But that is not the case here. So it seems that the exchange property is being violated here. And if I view the second option, then I do not find, yes, so except 4. But then second option clearly is not a Matroid because I do not have 4 here, and however I have 2, 4, and then 3, 4, etc. here. So
Yes.
this is not a Matroid. And third is that E is this one. So we have increased the universe of discourse, and I be the collection of all the subsets of E with K or the fewer number of the elements, then E and I together. So if I only consider K or the fewer number of the elements uh, as a member of the set, as a member of the family. So, but yeah, so K or the fewer number of the elements. Uh, but because the doubt is in the exchange property, because if I consider K or the fewer number of the elements, and some of the elements can be merged to result into the bigger set and having more than K number of the elements. So, uh, yeah. Because in the exchange property, there is always a possibility of growing the sets. And
Yes. So you are saying that this one is not a Matroid. This one is also not a Matroid, and this one you don't do not know because
so
you have seen that.
I'm sure that the second option definitely is not the Metroid, but the option 1 and 3 may not be Metroid in light of the exchange property.
Okay. So I don't know why this is not visible. It has become blurry. Let me check. I don't know. Let's do one thing. Let's have both the properties within our view. So you're able to see both the hereditary and exchange property.
Yes, yes, yes.
So now we are going to say a check. So first thing is that we have to check whether the empty set is part of the given family. So that check is trivially true. So this is also here. So let's first look at this of the first statement. Three statements. So B is, you have rightly concluded, is not a matroid. So this is false. And B is not a matroid because there is a family consisting of a singleton 1, and here is family 1 4. So the number of elements in this family is 2, and the number of elements in this family is 1. So this cardinality of this family is strictly less than the cardinality of this family. So it should be possible to add one element from this set such that, well, let's not take 1 4, let's take 2 4, 2 4 and 1. So it should be possible to add one element from this family to this family. So you pick one element from this family and take union with this family, and it should be part of the family. That is because of the exchange property. But 1 4 is here, right? Okay, sorry.
Even because of the heredity property also, since 1, 4 is a
Oh, okay,
part of
fine.
this,
Yeah,
yeah.
yeah. So if any hereditary property says that if there is a family B, which is a subset of a family. So if A is a family and B is a subset of A, then B should be a family. So 1 4 is a family. So any subset of 1 4 should be a family. So 4 is a subset of 1 4, but 4 is not there in the family. So the hereditary property is violated. So this is not a matroid. So, but for the first family, first check hereditary property. So, how many singletons are there? Four singletons. The universe size is four. So, all the singletons, possible singletons are here. The number of possible pairs is six. So, all the pairs are also there. Okay. So, hereditary property is definitely satisfied because from the pairs, if you take any subset, all the singletons are in the family. So now we have to check whether the exchange property is satisfied. So we'll consider two sets, any two sets of different cardinality. So for example, this is cardinality 0 set, this is singleton set. So trivially 2 union with the empty set is 2 and this is in the family, so this is not interesting. So let's take a singleton and take any pair. So with the singleton, you take one element from the pair that will give you another pair, and all the pairs are in the family, so that pair is also in the family.
No, yeah, where is that? Because if we consider 3 and 1, 4, then following the exchange property,
Yes.
uh, the cardinality of B is greater than the cardinality of A. So then there exists B. Uh, oh, I see. So it shows that it is not necessary for all the B's. So there must exist a single B. Probably it answers that question that A union B need not to be the element of the family, because there should be a single B. So like in this case, 3 and 1, 4. Uh, can we find one such? Yes. So there exists this element 1. So that 1 and 3, and this 1 3 is a part of the family. So yes, and that is how it is correct. So if we consider 3 and 3 4, then that element could be say a 4, and so 3 4 is already there.
Yes.
Yes. Yes, so
And
I
all
think
the
that yeah, we need not to consider say all the B's. Uh, yeah.
yeah, it should be possible to find one B
Yes.
from the larger set.
Yes. So now in light of this exchange property, yeah, so if we consider C, so C becomes difficult. And if we consider only K or the fewer number of the elements, uh, then if we, so it is not necessary that if we consider, say, one set having K minus one number of the elements, the other set is having K number of the elements, then one B should exist. So would be having that union would be having at the most K elements. So yes. So exchange property in any case is going to be fulfilled here for the option C. And now it is the matter of the following the very first property, whether phi is the element of I or not. So since we are considering K or the fewer number of the elements, so phi would always be a subset of this set. And regarding the heredity thing, so heredity thing is also going to be followed. Uh, because if we consider a larger set and if it is a subset of this thing, so then the subset would be element. Yes, so it will form a matroid then. All the
Yes.
three properties are getting fulfilled.
Yes. So we have verified all the three properties.
Yes.
Uh, so this is going to be matroid. So let me mark it true. But let me just repeat the argument which you said. So I is the collection of all subsets of E with K or fewer elements. So the empty subset is part of I. The first property is satisfied. Now consider the hereditary property. So consider a set A which belongs to the family. So in Arthur's family, okay. So suppose let me just take it. So suppose A is part of the family, then it means that cardinality of A is less than or equal to K. So any subset of A, master, let's say B is for any subset B of A. the cardinality of B is definitely at most the cardinality of A, which is again less than or equal to K. So B is definitely in the family because the cardinality of B we have shown is less than or equal to K. So the hereditary property is satisfied. Now look at exchange property. So consider two sets A and B in the family. Suppose A and B are in the family such that B has strictly more elements than A. So, so there is at least one element which is only in B but not in A. So first of all, since B is in the family, the cardinality of B is at most K, right? So the cardinality of A is at most K minus 1 because cardinality of A is strictly less than the cardinality of B. Okay. So that element, which is definitely there is an A because of the fact that cardinality of A is less than cardinality of B. So there is at least one element which is in B but not in A. So now even if you add, so even if you take the union of that element with B, the cardinality of that union is not going to be exceeding K, isn't it? So that is the reason we have the exchange property satisfied. So therefore, this is a matroid. Fine.
Yes.
Okay. So we can move to the next question. Just the next page. So I'll let you read the question. Okay, so this is the first question is not related to matroid. It is related to matroid, but right now we are only looking at it from the perspective graph. So we have a graph. Let's say it is S it is C and vertex it is V as usual. So every subset of an acyclic set of edges is also acyclic. That is the first statement.
So if we consider every subset of, say, a minimum spanning tree, or a spanning tree. So if we consider every subset of a spanning tree, will that be a spanning tree? So yes, the answer would be yes.
Okay, so why are you talking about spanning tree?
Because spanning tree is the acyclic subset of the edges of the given graph. So since here also they are asking that every subset of an acyclic set of the edges is acyclic. So I took a spanning tree as an instance. And now if I take any subset of a spanning tree, so that clearly would argument cannot form a cycle. So that will also be acyclic. So therefore, this seems true to me.
Okay, so maybe spanning tree is not required. So you consider a subset A of the edge set. Let A be a subset of the edge set such that A is acyclic. So now A is acyclic means there is no cycle in A, right? So because there is no cycle in A, so even if you delete some of the edges and found a subset of A, then that subset cannot have cycles either because you're not adding edges, you're only deleting edges. So when we are saying that subset of an acyclic set of edges, that means we are probably deleting some edges, or maybe we're taking all the edges, but we're not adding new edges. So unless we add new edges, how can a cycle get generated in an acyclic graph? It is not possible, and therefore any subset of an acyclic set of edges of G is also acyclic.
Yes. And regarding the second option, every subset of an independent set or subset of vertices is independent. So independent set comprises of all the vertices such that none of the vertex is connected to any other vertex in that set. So
Yes.
since none of the vertex is connected to any other vertex in that set, so if I take the subset of the vertices, so clearly the connectivity is already not there. So yeah, so the subset would also be independent. So therefore, this is also true.
That is correct. That is true. Let me mark it true. So an independent set is a set of vertices of the graph such that if you pick any pair of vertices, there is not an edge. So such an edge. So there is no edge between any pair of vertices. So if you take a subset of the vertices, a new edge cannot be generated because we are not adding edges. We are just, so this is an independent set because there is no edge between any pair of vertices, then any subset of the independent set is also going to be independent because the fact that there is no edge between any pair of vertices in the subset is still true. Okay. Next.
Regarding this next option, so if I1 and I2 are two sets of the edges, both acyclic, so they are not forming cycle. And if the cardinality of I2 is greater than I1, then some edge X, which is there in I2 and not in I1, can be added to I1 to produce an acyclic set. So if it is not forming a cycle in I2, if it is not forming a cycle in I2, then uh, is this necessary that it is not going to? And if I take some age which is not in I1 and which is there in I2, and if I take that age, so yeah, and that is not forming a cycle, but this is not necessary because quite possible that the dynamics of the graph could be such that if I remove that age, so some of the age, one age may be taken from I2 and that may make I1. That can be added to I1 to produce an acyclic set.
Correct. So you understood the question.
Yeah.
So there is some set of, so we have this graph and I1 is some set of the edges. So let us say we mark it's so there I1 is a set of acyclic edges. So there is no cycle. So let us say this is I1. Okay, let us also draw I2 in some other color, let's say red or maybe green. So it is not necessary that I1 and I2 are disjoint. So maybe it is not so we do not know whether it is disjoint. It may or may not be equal to phi, but we are not imposing anything that whether I1 and I2 should be disjoint. So maybe there is some edge which is both in I1 and I2. So maybe this is both in I1 and I2. So maybe there is one more edge, which is maybe this is also in I2. But I2 has strictly more number of edges than I1. That much we know. And we are claiming, the statement is claiming that because I2 has strictly more number of edges than I1, then there must be one edge which is in I2 but not in I1, which is uh, exclusive to I2 but not in I1. That can be added to I2 such that, that can be added to I1 that can be I2, I1, such that even after the addition of that edge, I1 remains acyclic. So in this case, let us say the blue edges are in I1. So how many blue edges? 6 blue edges are there. And let us say the green edges are in I2. So how many green edges? 1, 2, 3, 4, 5, 6, 7, 8. So 8 green edges and 6 blue edges. So in this case, there is this one green edge, or maybe this green edge, either of these two you can add with the existing I1, and that is still going to be acyclic. So question is, irrespective of what is I1 and I2, are we always going to find such an edge in I2 that can be merged with I1 without creating a cycle? So we do not want to introduce a cycle.
Uh, yes, but the proof, I mean, is not that much convincing. The only thing is that we are, it's okay. It is following the common sense, but
No, we have not proved anything. We are just asking. So we'll prove it now. So we
yeah,
haven't
okay.
proved it formally. So this is just for an illustration I have drawn this. So let's do one thing. Uh, so consider any set of edges. So if we say that we have an acyclic graph in n vertices, let's take a detour and let me ask you a separate question. So if I say that there exists, let's say we claim that G is a graph in n vertices, and we also tell you that G is acyclic, then what is the maximum number of edges in G?
Okay, so the number of the vertices are n number of the vertices. So the number of the edges would be n minus 1.
At most, exactly.
Most, yeah.
Yeah. So now we are saying that okay, we have an observation that if you have a graph in n vertices, additionally if the graph is acyclic, then there can be at most n minus 1 edges, because if you add one more edge, then you will be forced to create a cycle, isn't it? So in a tree. So for example, this is a connected tree. 1, 2, 3, 4, 5, 6 vertices, and 1, 2, 3, 4, 5 edges. Now there is no way you can add one more edge without creating cycles, right? So it
Yes.
is one connected component. Okay. So now what we are going to do is that we are going to consider the graph. Let me just, so this is the proof sketch. So consider the graph induced by the vertices of I1. So for example, in this case, so these are the vertices of I1. And you consider all the edges that are in between these vertices. Okay, so that will give you an induced graph. So, but that it is not necessary that there is only one connected component in this induced graph. There can be multiple connected components. So you understand what is a connected component. So connected component means a connected component is a set of vertices. It's a set of vertices such that there exists a path between every pair of vertices. in the set.
And what this graph is, which is induced by by the vertices of I1?
So I1 is a set of edges. So when I say vertices of I1, vertices of the endpoints of the edges in I1. So vertices of I1 is nothing but the endpoints of the edges in I1. So I am saying that I1 is an acyclic set of edges, but it is not necessary that I1 is a single connected component. For example, this green edges could be in I1 as well as this red edges could also be in I1. Okay. So I1 is what? I1 is by definition. Let's look at the question once again. So I1 is a set of edges that is acyclic. That is the only thing. And I2 is also a set of edges that is acyclic. And I2 has strictly more edges than I1. So maybe there are multiple connected components. When you look at the graph induced by the endpoints of the edges in I1. Now, we identify that in each of these connected components, which are the edges which are in I2. Okay. So maybe some of the edges are in I2. So let's take red. No, red is already used. Let's take pink. So maybe this edge is in I2. There was an edge which is also in I2. This edge was also in I2. There is an edge which is this one in I2. So I am saying that identify those edges in the connected components separately, which are in I2. So pink is mark edges in I2. Okay. Fine. So how many pink edges are there in this connected component that we can bound using this property?
So, like in this case, by the way, there are, I mean, the number of the pink edges is either less or equal to the number of the green and the
Exactly.
red here. Yeah.
So
So we'll have to
because,
include more.
yes, go ahead.
So we'll have to include some more pink edges here because I2 is strictly greater than I1. And here
Exactly.
in I1 we have green and red edges.
Exactly. So the point is, if you consider any connected component, so if this connected component has k vertices, then the number of edges in I1, the green edges is k minus 1. That is known to you because this is a connected component. And because this is a connected component, the edges which are in I2 in this connected component is at most k minus 1. Otherwise, there would be cycles. Because I2 itself is acyclic, so we cannot introduce any cycle in I2. Therefore, the edges in I2 which are part of this connected component is going to be at most the number of green edges, the number of edges in I1. And that is true across the components for any component. But then the number of edges in I2 is strictly more than the number of edges in I1. So that means there are other pink edges which are outside of the components. So that means that at least one pink edge, at least one edge exists. There exists at least one edge in I2, which is not in I1. So that edge you include with, so that edge is outside of all the connected components in which I1 is participating. So that edge, even if you include that edge with I1, is not going to introduce a cycle.
Yes, right, right.
So there must exist this one connected, at least one edge in I2, which is not in I1. And this edge is outside of all these connected components. So because it is outside, both the endpoints are outside. So how can addition of this edge with I1 lead to a cycle? If you want so if you added an edge between same vertices in the component of in one component of I1, that would have led to a cycle. Okay, but this edge is maybe so this is possible. So maybe this edge was like this. So one endpoint is one component, other endpoint in the other component. But whatever that edge is, which is in I2 but not in I1, is such that both its endpoints are not in only one component. So therefore, addition of this edge is safe in I1. Safe in the sense it will not lead to any cycle. That is the argument.
Yes.
So this is true. So if I1 and I2 are two sets of edges, both are cyclic, number of edges in I2 is strictly more than the number of edges in I1, then some edge must exist which is in I2 but not in I1, and that can vary to I2 without producing a new cycle. So this is true.
Yes, and the meaning of the next is not that clear, that there exist two maximal acyclic subsets, I1 and I2 of the edges, such that there exist two maximal acyclic subsets such that I2 is strictly greater than I1. So there exist two maximal acyclic subsets.
So maximal means that with the subset, if you add one more edge, then no matter which edge you add, that will lead to a cycle. So that is the
Yes,
meaning of maximal.
yes. So like saying, yeah. So uh, I'm unable to think, but probably the solution could also be based on this same strategy that in one acyclic, say we have n number of the vertices in I1, then maximum there could be n1 minus 1 number of the edges, and in I2 if I have m, so then there would be m2 minus 1 number of the edges, but
Okay.
then n plus m is the total number of the vertices, so there would be how many n1 plus uh, n1 plus n plus n plus m minus 2 number of the edges, but then in total there should be n plus m minus 1 number of the edges, so at least one edge is remaining. So whatever is remaining, that will become the part of the I2.
So are
I
you
think
concluding true or false? What are you concluding?
so. Yeah, so I conclude this that so since the number of the edges are less here than the number of this thing, so yeah, so yes, so this is true, this is true, this is true, this is true, uh, this is true because we assume that okay, there are n number of the vertices in I1. So then there could be maximum n minus n minus 1 number of the edges. And let us consider say m number of the vertices in I2. So there would be at the most m minus 1 number of the edges. So if we take the sum, so then the sum number of edges came out to be n plus m minus 2 number of the edges if both are acyclic. But then if we consider uh, total number of the edges in an acyclic thing, no, this is not substantial. The logic is not that
So let's
substantial.
do one thing. Let's have some notation. So we are saying that okay, there exists two. So you were what I understood is that you were taking that okay, you said that okay, let us say that the coordinator of I1 is something, N1, coordinator of I2 is something, N2, so N2 is more than N1. And then you were saying that okay, because the coordinator of I1 is N1, Therefore, you are trying to relate the number of vertices in the components of I1 with N1, right?
Yes.
And then you said something like the addition of N1 plus N2 is something. I I was not able to follow, but I can help you if you just say it once again what you were saying.
Yes. So I said that in I1, say there are n1 number of the vertices. So
Yes.
this is not the cardinality of
No, no.
I1, but
So you were saying
vertex.
that okay, so there are number of endpoints of the edges in I1 is N1. That's what you're saying.
Yes, yes, yes.
Uh, Fine. Okay, so
So
let's
then,
do
yeah. So then number of edges would be
let's
number.
say I define a function. So f of I1 is N1 means the number of vertices of the endpoints of I1 is denoted by f of I1. Okay. So f of
Yes.
I2 is N2 and but we do not know if N2 is greater than N1. So fine, we define this. So what is the next thing you were saying?
So next is that so the cardinality of I1 is bounded by n1 minus 1,
Yes, that is
and
true.
the cardinality of I2 is bounded by n2 minus 1,
Okay.
and total number of the vertices would be n1 plus n2. So in any case, the total number of the edges would be bounded by the,
It's
but this is not necessary that the entire graph, uh, yeah,
maybe some of the edges are not in I1 and I2, but they are in the connected components of the induced graph.
yes. So
So,
I mean, what's the meaning of the graph induced by in the previous option also you mentioned this, the graph induced by the
so,
vertices. So what does it mean?
so when we say that you have a vertex set U, which is a subset of the vertex set of the graph, then the
Oh,
graph induced by U is the graph where you take all the vertices in U and all the edges that lie between any two vertices of U.
okay, okay, okay. All,
For
all, all
example,
those all those edges which were the part of the original graph and whose endpoints are there in U.
yes, yes, that is right.
Okay,
For example,
okay,
in this connected component, so these edges were in I1, the pink edges were in I2, but there could be other edges which is present in this connected component, but which are not in I1 and I2. Maybe there are other edges. So this edge, nobody is ruling out this edge. If in the original graph this edge was there or this edge was there, then that is part of this connected component, but they are neither in I1 nor in I2. So this is
okay,
induced by the vertices which are endpoints of I1.
okay, okay. So now that so there exist two maximal acyclic subsets of I1 and I2. So if I consider two maximal acyclic subsets, only two, there could be more.
Yes, yes. It could
There
be
could
more.
be more. So
So maximal asset, let's take an example. So this is a graph. No, this is a quick graph. Let's do one thing. So can we draw a graph where there are more than two maximal acyclic subsets of edges? That is what I'm thinking. Let's do one thing. So let's copy this statement once, and then we'll go down. Oops. Just remove this. This is now it will work. I'll just copy this portion. There exist two maximal acyclic subsets I1 and I2 of E such that cardinality of I1 is more than cardinality of I2. So it is making a claim that okay, there is a graph, and in this graph there are two subsets of edges I1 and I2, and both of them are maximal acyclic, but their cardinalities are different. Is this possible? Or whenever you see a maximal acyclic subset, its cardinality should be same as the cardinality of another maximal acyclic subset? That is the question. Let's try to draw some example. I'll just try to make up some example. Let me think. Right. So in this graph, the vertices are 1, 2, 3, edges are, let us say, A, B, C. Okay. So I1 is, let us say, A comma B. Can you add C?
I1 is A comma B, and if I add C, no, I cannot.
You want a subset of edges which is acyclic maximal, means even if you add one more edge, a cycle will be formed. So with A and
Yes.
B, you cannot add C because a cycle will be formed. So BC is also a maximal acyclic subset, and CA is also a maximal acyclic subset. But the point to note is that all these subsets are of equal size. So in this statement, the claim is that given a graph, the maximal acyclic subsets are of equal cardinality, or there is in this statement the claim is there is at least one pair of maximal acyclic subsets whose cardinalities are different. So I think you have a better clarity on the question now.
Yes, the language is slightly actually not that clear. This says that there exist two maximal acyclic subsets of E, and moreover, they are talking about not only the acyclic subsets, but then their acyclic subsets are the maximal ones.
Exactly.
Uh, so since the acyclic subsets are now maximum, so I mean, how is that possible that the cardinality of the other one is greater than the I1?
Okay, then
Uh,
we can mark it false. If that is the intuition, we'll mark it false. In fact, this is false.
so if I go by the literal meaning of the term maximal, then uh, how can we have two things which are maximal and differ by some amount?
No, no, that
So
is
so
possible.
maximal means that we can have we do not have unique maximum. That is
Yes.
what the meaning of the term maximal is. But then if we have maximal, so it stands that both are of the same cardinality, or then only they are maximal.
No, no, that is not true. Maybe there could be so in this setting is it is true, but there could be a setting where two things are said to be maximal, but they have different cardinalities. That could be possible. So maximal does not mean that. So what you are thinking, the way you are analyzing is that if there is a unique maximum, then we call it maximum. Otherwise, if there are two different maximums of the same cardinality, we call them maximal. But that need not be true. But in this case, it is true that there cannot exist two different maximal acyclic subsets that have different cardinality. In fact, in this example also, we are seeing that there are three different maximal acyclic subsets and their cardinality are all same, equal to 2. Isn't it?
So what if we draw another edge from 2 to upward, say, let us call that as the vertex 4. Yeah, so now we have uh, one acyclic subset as 1, 2, and then 4
No, no, acyclic subsets are edges, sets of
edges.
edges.
Yeah. So
So let's call it
1,
D. This is D.
yeah, yeah. So it is A, B, and then D.
Yeah, you can
So
add D. To each of them, you can add D.
so I have one acyclic subset as ABD, and the other one is only C and then B, only C and B. C.
But
If I do not include D here,
then it will not be maximal because even after you include D, acyclicity is maintained.
so then what is the meaning of maximal here then?
Maximal means that it is not possible to add even one edge without losing acyclicity.
Oh, I see.
So maximal means that is the maximum number of edges you can add without creating a cycle.
Yeah, okay.
So we haven't proved, we have an intuition that the maximal acyclic subsets should be of same cardinality, but we haven't proved anything. Let's try to prove it why this is false. So
Mhm.
let's read the previous statement what we have proved. We have proved that if I1 and I2 are two sets of edges, both acyclic, and I1 is I2's cardinality is more than I1, then there is some edge in I2 but not in I1 which can be added to I1 to produce another acyclic set. Okay. So that it means that if I2 is, so it means that now we'll apply. So we have proved this. We apply this here. So we want to prove that this is false. So first assume that this is true. Then we will try to get a contradiction. So assume that this is true. So assume that I1 and I2 are in fact maximal acyclic subsets of edges and cardinality of I1 is less than cardinality of I2. Then we apply the statement of the previous thing to I1 and I2. So that means there is some edge X which is in I2 but not I1 that can be merged to I1 to get another acyclic set. So that means I1 is not maximal. The maximality of I1 is contradicted.
Yes.
So therefore, this statement is false. So this is a
Yeah.
proof by contradiction. And the instrument that is used to get the contradiction is this statement, this claim, which we have proved.
Mhm. Yes, yes.
So now we have proved that I1 and I2, if they are maximal acyclic subsets, they are of same cardinality. Okay. Okay, so I think at this point we can take a break. It's 1 hour already.
Yes, yes, sure.
Okay.
There is a power cut here, so I do not know till what time my mobile will give me hotspot.
Okay,
Let me see.
okay.
Yeah, yeah.
So do you want to continue? I can continue. It's up to you.
So we can take, as usual, the break of 5 minutes.
All right, fine. I will be
Yeah.
back by 7:09 or 7:07.
Yes, yes.
Are you back?
Yes, yes.
Okay. So is the power back or is it still load shedding?
Uh, yes, it's still I'm using my mobile only. Power is gone.
Oh, okay. All right. So yeah, so let's see how long we can continue.
Yeah.
So look at the next one.
So next one seems to be difficult. I read this multiple times. So it says that the maximal acyclic subset I of E counts the number of the vertices in the given graph, and minus the number of the connected components in the subgraph induced by I. So I'm doubtful about the subgraph induced by the edges, though I understood the subgraph induced by the vertices.
Subgraph induced by the edges means subgraph induced by the endpoints of the edges.
So, what does it mean? Like, say, if you can give a small example, or if you can draw a graph, or
So let's do one thing. Let's copy this statement. So consider a graph. Okay. So maybe it has a couple of components. So let us say this is a graph. Then when I'm saying that a subgraph induced by some set of, let us say I some set of edges. Let us say the red vertex, the red edges are in I. Okay. So maybe there is an edge I should. So these are four. There are four edges in I. Let us say. Then the subgraph induced by I is the subgraph induced by the endpoints of the edges in I. So how many endpoints are there? So every so four endpoints here, and here only three endpoints. Okay. So now you have to take all the original edges which are between these endpoints. So which one shall we take? We'll take this, take this, take this, take this, take this. Right?
okay, okay.
So the subgraph induced by I may contain more edges than the number of edges in I.
So, but then how will it make a difference in the number of the connected components? Uh,
So that we'll see. Let us see that. So, so it is statement is the size of a maximal acyclic subset I is nothing but the number of vertices minus the number of connected components in the subgraph induced by I. So consider this example only. So,
mhm.
so in consider the subgraph induced by I. So this is these three edges is one component and these three edges is another component, right? So
Uh,
this is
yeah,
the sub
with
this
is here, yeah.
so
But
these four
yeah, yes,
not
yes,
these four vertices are giving rise to three edges and these three vertices are giving rise to three edges. So this is the entire subgraph induced by I.
yes.
And There are two connected components. This is one connected component. This is another connected component.
Mhm.
So in this case, the size of I is what? How many edges are there in I?
Uh, there are four edges.
Yes. So I is just the red edges. Four edges are there in I. On the other hand, in the connected component, in this, so this is one connected component. How many? The number of vertices minus the number of connected components in the subgraph induced by I. So first of all, you have to count that how many vertices are there in the subgraph induced by I. So 1, 2, 3, 4 here, and 1, 2, 3 here. So 3 plus 4, 7. So 7 is the number of vertices in the subgraph induced by I.
Uh, oh, I see. Yeah. So we have, yeah, it's right. Yeah.
Minus the
Mhm.
number of connected components in the subgraph induced by I. So there are two connected components. I'm not sure why it is not matching. Let's what have I done the right thing? The size of a maximal acyclic subset I of E counts the number of vertices minus the number of connected components. So there are, oh, there are actually how many connected components are there?
But then here they are asking the size of maximal acyclic subset of E.
Oh, I
Uh,
see, I see. So here I is not a maximal acyclic subset, right? Okay, in
yes.
this case, that is the reason it is not matching. So let's try to prove it. So
Yes.
let's try to prove it formally instead of taking examples. So I took the example so that it is easier to visualize. In
Yes.
this
Yes.
case,
Now the
it is
idea
not
of
matching.
this is, yeah, clear to me.
Okay, now consider, so if I is a maximal acyclic subset of E, so then the number of vertices minus the number of connected components in the subgraph induced by I. So now consider the subgraph induced by I. So in the subgraph induced by I, let us say there are multiple components. So in this case, there are four, and let us say the multiple components are there. I don't know. Some k components are there. In the subgraph induced by I, so because I is a maximal acyclic subset, so each of these components are also uh, full, that we have seen that. So if in this component there are mod C1 vertices, then in this component there are mod C1 minus 1 edges, because of the fact that I is a maximal acyclic subset, right?
Yes.
So now we can count left hand side is the size of, so what is the, how many edges are in I? So mod C1 plus mod C2, oh sorry, summation mod Ci minus, so let's write it in summation form. So we're going to take the sum of all these things. So I from 1 to k. This is the total number of edges in I. So C1 minus 1 plus C2 minus 1 plus Ck minus 1, dot like that. So this is the, okay. So how many vertices in all these components?
So there are C1 plus 1 number of the vertices. Sorry, C1 minus 1 number of the edges. So C1 number of the vertices.
Okay. So overall,
C1 so in total
we
NC, say the summation of CIs, yes, these many number of the vertices are
yes, yes. How many connected components? K.
there. K number of the connected components.
So if we minus the number of connected components, this thing minus K. And this
Yes,
is also, if we, so there are K terms here. So summation
yes,
Ci, for every term there is a minus 1, so minus K.
yes,
So therefore the number of edges in the maximal acyclic subset I is nothing but the number of vertices in the induced subgraph minus the number of components. That is the proof. So in this case, the numbers were differing because I was not a maximal acyclic subset, because we could add other edges to I. So this is also possible to add this, and this is also possible. This is also possible, isn't it?
yes.
But yeah. So it was a good exercise for us to do. So we have realized that if the cyclic substitute we're taking is not maximal, then this statement may not be true.
Yes, yes, yes.
Let's go to the next one. So we'll mark this as true.
Let F be the set of the S set of the G. So F is a collection of all the edges of G, which are acyclic. Then E comma F is a matroid. So E is fine, and then what about this F? So F is which are acyclic. So no edge is this acyclic if I do not consider any edge? Uh, will it be
Yes,
considered as okay, okay. And if I pick an edge, if I pick all the edges individually, acyclic. So if I take two edges, and if I pick two edges, would be acyclic. But if I go beyond two, then quite possible. But even if so, F is a set of S set of G which are acyclic. So but then this is given that F is a collection of only those edges which are acyclic. So if they are acyclic, uh, so if I pick say 1 comma 2, and if I pick so heredity property is definitely true here, is true here.
yes,
There is no doubt. But then regarding the exchange property, that if I pick if it is acyclic, is not forming a cycle, and if I take that, so yeah, so this will, yeah, I think that this is true. This is true. And this is true because even the exchange property is going to be followed. The reason being that if we consider a bigger set, which itself is acyclic. So now we have been given two acyclics. One is smaller and the other one is the bigger. So following the previous rule, we can always include a smaller one into we can always include I mean an element of the bigger one into the smaller one, and that would still remain as a cyclic only. So exchange property is also followed. Probably it is in line with the conclusion we draw for this option number C. So this seems true then.
yes. So we have seen this option C. So here we have said that, okay, if there is a bigger set of acyclic edges, then so if there are two sets of acyclic edges, one is strictly bigger than the other, then we can exchange an element from I2 to I1. That means we can pick an element from I2 and give to I1, such that the resulting set is also a cyclic set. That we have proved. And because of the truthfulness of this statement, uh, the exchange property is satisfied in this case. Okay. And hereditary property is vacuously satisfied because any set of acyclic subsets, oh, this is property one. So every subset of an acyclic set of edges is also acyclic. So because of A, hereditary property is satisfied, and because of C, the exchange property is satisfied. And if you take no edges, an empty set of edges, that is vacuously acyclic, that is also in the family. So therefore, this is a matroid.
Yes. And in the next one it says that F be the set of the vertices of the G which are independent. So F be the set of the vertices which are independent. Okay. Phi, if I do not consider anything, would be independent.
Yes.
And if I take all the vertices in isolation, then would be independent, obviously. And since F is the set of the vertices which are independent, so any subset of the independent set would also be independent. And we have seen this in the previous
Yes.
example also. And if we add something from an independent, uh, but then that will still remain as independent only. So, and we did this earlier also. So this is true in my view.
So are you convinced about the exchange property?
So regarding the exchange property, that if I consider a larger independent set, then there would be uh, independent. There is no edge in between the vertices of the larger set of the vertices. So yeah, and yes. So but then since F is, so there is no guarantee as such, because if I pick there is, I mean, what's the guarantee that all the, I mean, we do not have edges in between the vertices of the bigger set. And what if both the sets are disjoint? Both are the disjoint set of the independent vertices. And if I pick an vertex from there and include here, then will it still remain independent? Uh, will it still remain independent? Not necessary, not necessary. But then this does not mean that I can never find any vertex which will uh, keep the smaller one independent as well. So I think that this is true.
So so the way to so the way to verify the exchange property. So first of all, the hereditary property is vacuously satisfied because if you have a set of independent vertices, any subset of it is also independent because we are not introducing any edges. This is property B, which I already said that every subset of independent set, uh, every subset of independent set. Okay, this is not necessary. So we have already seen this. So every subset of an independent set of vertices is independent. So hereditary property is vacuously satisfied. And phi, the empty set is also an independent set that is also satisfied. Now the question is if there are two independent sets I1 and I2 such that mod I1, the number of vertices in I1 is strictly less than the number of vertices in I2, can you pick one vertex which is in I1, which is in I2 and give it to I1 without destroying the independence of I1? And is it always possible given any I1 and I2, which is independent sets? That is the question. So if we have to prove it, then we have to show that, okay, so how do you prove this?
So yeah, so if I prove it, say by the contradiction kind of the thing, then if I include all the vertices of the I2 into the I1, So if I include all the vertices of I2 into I1, uh, and I1 and I2 both are independent.
If you want to,
So
yeah, go ahead.
yeah, no, I mean, contradiction is not going to give something fruitful. But I was under the impression that I just need to show that there exists one vertex in I2 whose inclusion in I1 will maintain the independence. So there exists one vertex in I2, at least one vertex in I2, which does not form, which is not connected to any vertex of the set I1.
So in the previous case, to prove the exchange property, to prove that exchange property is true for this kind of a family, we use this. So
Yes.
we were able to show that there is one edge. So if you remember the picture, we were able to identify one edge which was safe to be given to
Yes.
I1 without losing a cyclicity. So we have to be able to identify one vertex which is inside of I2 that is safe for I1. So we have to do some kind of construction if we want to prove it. Okay. So we will consider some I1, some I2. Then in this I2, in this set of vertices, or maybe I1 and I2 are intersecting. That is also possible. So you have to identify one vertex which is in I2 that is safe for infusion to I1 without losing independence. That kind of thing you have to show. Okay. Otherwise, you can try to prove it false. If you want to prove it false, then you have to show a counterexample. Then you have to show a graph such that there is a set of vertices I1 which is independent and set of vertices I2 which is independent, and mod I2 is strictly larger than mod I1. And then you show that there is no vertex in I2 which you can give to I1 without losing the independence of I1. So you have to show an example. Okay. So if you want to prove it false, you have to show a counterexample to this statement. Okay.
Yes.
So let's try to. So what do you want to do?
So I think that the counterexample is difficult to come up with the counterexample. So better we go for the first one.
How about this?
So so
So this is an independent set. B and A and C are also independent sets. So B is an independent set. I1 is this, and these two are I2. So can you take either A or C and give it to B and merge it with B to get an independent set?
so now this B is no longer. So if I add A and C to it, so then this is no B is no longer independent now.
Yes.
Yeah.
So this is a valid counterexample.
Yes, this
Yes.
is a valid counterexample.
Yes. So you can neither take A and merge with B to get an independent set, nor you can take C and merge with B to get an independent set. So even though the coordinate of I1 is only 1 and the coordinate of I2 is 2, there is no way to guarantee that there is one element which you can exchange. So the exchange property is not satisfied.
Yes.
This is not true. So I spent a lot of time thinking that whether we can prove it. So this happens quite often in math or theoretical computer science, that you try to prove something, you spend a lot of effort, and then you find a counter example, and then you are assured that there is no proof of
Yes.
the truthfulness.
Yes, this is the goodness of theoretical computer science actually.
Yes, yes. So I could have given you the example immediately, but I thought that this exercise of thinking would be beneficial. So I did not give the example. It was a very straightforward example.
Yes. So let G be a directed graph and I be the collection of the subset of the edges without any directed cycle. So I hope that the directed cycle means the cycle only, or do they have any specific meaning of it? Uh,
Directed cycle means a set of edges, ordering of the edges. So sorry, what I say. So what is a directed cycle? So let me copy this. There is no space here. What I will do is I'll just write down the question. So go down and write down the question. Be a directed graph, and I be the collection of subsets of edges without any directed cycle. Question is, does P comma I form a matroid? So this is a statement. So I have to tell you whether it is true or false. So this is a statement. So
yes.
directed,
Yeah.
so directed cycle is a sequence of vertices such that there is a directed edge between Bi to Bi plus 1. There is a directed edge from Vk to V1 also. So
Yes. Yes. So here E is and what this okay here I is the collection of the subsets of the edges without any directed cycle. So clearly phi is the element of this, and so all the vertices in isolation are the part of it. And
yes,
if I've been given two paths which do not form a cycle, so if I consider a path of the length k and the path of the length 1 only, so clearly the length of the path k is greater than the path of the length 1. So this is not necessary that if I okay, so if I consider a path of the length k minus 1 and the other path of the length k, so um, then quite possible that if I pick one of the age of k, heredity property is going to be satisfied. Though that is not the issue here. I think the only
yes,
problem is with the this exchange property. So if I consider a path of the length k and the path of the length k minus 1, then is it necessary that there exists an edge in the in the path of the length k, which is not going to form a cycle in k minus 1. So uh, yeah, that we can find uh, such a is we can always find. So yeah, so like see here, so if we so these are not forming a cycle. uh, yeah, so if both are independent, so then such a path can always be find out. Even though I could difficult to find a mathematical formulation of this, that can we always find
yes.
an age,
So
and
let's
which
try
is
to
not.
get a word.
Yes, yes, please.
So you're saying that it is not straightforward to prove the exchange property because if you consider two subsets of edges, I1 and I2, where I2 is larger than I1, then how do you identify that edge in I2 that can be safely added to I1 without forming a cycle?
Yes.
So whereas in the if you look at the previously we have said that this is a matroid. So we're able to say in an undirected graph, acyclicity was sort of so the acyclic property was giving rise to a matroid, but here it is not very clear. So in this case, we were able to prove something like this, that we identified one edge which is safe for I1. That means that was not leading to a cycle, if you remember this picture.
Yes.
But it was an undirected graph, and we could show this property. But it is not very straightforward here. So let's try to think in the other direction. Let's try to see if we can get a counter example. If we can get a directed graph, and we will identify two sets of edges, I1 and I2, such that there is no uh, edge. Uh, so there is no edge in I2 that is safe for I1. So where safety is defined by you know this formation of directed cycle. So a directed cycle has length 3 at least. So it's a directed triangle.
So, so what if we take I1 and I2, something like, say, consider one portion of the graph as G, and make the remaining edges, say, one set of the edges as the part of I1 and remaining edges as the part of I2. Like in this case, if we consider, say, in this example, in this graph we drawn here, so 1, 3, and 5 as a part of the set I1, and whatever remains becomes a part of, say, I2.
So
So
you
like,
mean so I2 is, let us say, larger than I2, I1.
Yes, so in this case, I1 will become larger than I2, doesn't matter. So I1 here is say 1, 3, and 5, and I2 becomes say 2 and 4 then. So now at least we are sure that since one portion is, so basically we have split here a graph into two ways in such a way so that one portion is the inverse. What should I call this? This 2 and 4. Uh,
You want 2
one,
and 4, and you want 1, 3, 5, and 2 and 4?
yes, 1, 3, 5, and 2 and 4. So that 1, 3, 5 is one portion of the graph. Let us call this as G. So then, or let's call this as what? Uh, V kind of a thing. And then the remaining one, which is whatever remains, will come into this. So that we are forced to form a graph.
So this, how does this qualify to be a counterexample to the exchange property?
Okay, so like say this I1 is the collection of all the non-cyclic thing, non-cyclic direct thing, and the I2 is also non-cyclic direct thing. And now if I add any of the edge here in I1, if I add any of the edge of I1, say 1, 2, and then 4. Oh, I see. 1, either I add 3 or I add 5. So this is not the right counter example. And yeah,
I should have thought about it beforehand. Let's do one thing. It will take, maybe it will take me more time to think about it. So this is not a Matroid. We have to show the counterexample.
uh, okay. And I have one related question here that I have heard of this Matroid thing in greedy method,
Yes.
greedy strategy. But I do not know. I mean, why do we use Matroid there in the greedy? Because often this Matroid thing is skipped while teaching greedy paradigm.
Yes.
So can you shed some light probably or somehow I mean how this thing is related to that greedy way of doing the things?
So maybe we can take some concrete example. So, so what are the problems you have solved using greedy? Have you seen the maximum independent set of intervals question?
Yeah, so yeah, task scheduling and
Yes, yes. This is the same thing, job scheduling.
scheduling, yeah,
So if you do job scheduling, unweighted job scheduling,
yeah,
then these are the jobs, you have these jobs, and each of these jobs are equally weighted. Okay. So these are sort of durations of the job. So when I say, so maybe this is 9 a.m. in the morning to 10 a.m. in the morning. So I have shown this as an interval. So that's how we do. So what is the input? The input is a set of jobs and their durations. And the question is how many jobs you can perform without overlaps. What is the
yes,
maximum number of jobs you can perform without overlaps? Okay, so maybe
yes,
this job is starting at 9:40 and this is going till I don't know 11 a.m. So these are the possible jobs, and you as a person, or suppose there is a machine that can only do jobs one at a time. Therefore, you would like to do jobs that are non-overlapping. Okay.
yes,
So in this case, what they identify is that whatever is the optimal solution, that is, whatever is the optimal set of jobs that you can do, the maximum number of jobs, the maximum set of jobs you can do, it is always possible to have one particular job in the optimal solution. And that job they identify to be the job that ends first. So that is the greedy rule they use.
yes,
So in this case, the job that is ending first is this. So these are the start time and end times. So if you sort the jobs in increasing order of n times, then you will get an ordering. Then the algorithm is you sort the jobs in increasing order of their end times, and then you pick the one that finishes first, and then you discard all the jobs which are intersecting this job. That means if you are doing this job from 9 to 10, then this job you cannot do, which is starting at 9:14 and is overlapping with 10 a.m. job. So to
Yes.
discard this. Then in the remaining solution, in the remaining instance, you again find that job that finishes first. So like that you will proceed. So the
Yes.
exchange, there is something called exchange property in the, say if you look at the proof of correctness, if you look at the proof of correctness of this greedy rule, so this greedy rule is just one of the greedy rules. There are many different greedy rules you can apply. For example, somebody can suggest that why don't you pick that job which is shortest? Because I have an intuition that the shortest job, if you pick, then you are left with more bandwidth and you can accommodate more jobs. But that doesn't work. So the reason that this job that finds ends first works, that this greedy rule works, is because of the use of the greedy property. So if you look at the proof, then they will invoke this property that whatever solution, suppose if somebody claims that somebody claims a solution and somebody says that okay, this is the best solution we can get, then somebody can remove one job from the solution and pick this job which ends first. So suppose in this solution, this job that ends first is not there. Suppose this is job one and somebody has not picked job one, then they show that okay, you can pick job one and remove one job from here, and that will also be a valid solution. So it acts like a matroid because the exchange property becomes true. And there is a with matroid, uh, generalized argument can be given for that is applicable to multiple problems, that you show that okay, this problem is reducible to a matroid, and then you show that because of the exchange property, finally what you are going to get is an independent set. In fact, so this all the questions that we are looking at, so this is called the universe, and this family I is generally called the independent set. So because
Okay.
of the way matroid provides you an unified way of arguing the correctness and analysis of the greedy algorithms.
Okay. Yes. This is interesting thing. Yeah. Because many times it is this Metroid portion is skipped. I mean, in
Yes.
many places. Yeah.
Yeah, so if you just in light of today's class, if you just remember that these three matroid axioms that we started with, then if you read the analysis of the greedy algorithms using matroids, then they will focus on this exchange property, and then you will be able to follow the analysis. And the analysis is abstract, but is nice in the sense that it is applicable to many problems.
Yes.
Okay. So I think that okay, so this is not a matroid, but I'm not able to give you a counterexample immediately. Let's do one thing. We'll skip it for now. We'll go to the next question in the next 5 minutes. You can solve more questions. I will give you a counterexample soon, or maybe in the next class. So let's look at the next one. So we have 5 minutes. Okay, so this is of slightly different flavor. So maybe we will have time for only one or two. So you are given a matroid. So there is this universe and there is this set of families. So if there is a set C, which is a subset of the universe, such that it is a minimal dependent set, then it is called a circuit. Or the other way around, it is called a circuit if it is a minimal dependent set. Okay.
So
So
what this minimal dependence set is?
yes. So as I said, so there are two tuples in the matroid definition. So this is the universe, and this is a set of families. The family of sets, subsets of the universe. This is also equivalently called, so each member in this family I is also equivalently called independent set. Okay, so in our case, what is the kind of matroid we have seen? So we have seen the graph and a set of edges I such that every I1 in I is an acyclic, is a set of acyclic edges that we have seen. So let's do it from this perspective. So what we said is that uh, so we were talking about maximal. What is this term we used? We said maximal acyclic subset. So we said maximal acyclic subset, and we said that maximal acyclic subset means if you add any edge to this existing subset, it will lead to a cycle. Okay. Now the term that we are looking at is minimal dependent set. So that means that in this case, you have a cycle, and this cycle is called a minimal dependent set if it cannot be minimized further. Even if you delete one edge, it will no more be a cycle. You understand what I'm saying? For
Yes,
example,
so this will become independent then.
yes, for example, this is not a minimal cycle because there are two cycles. Even if you delete one edge, the cyclicity is still remaining. So you want to kill all the cycles. So a minimal dependent set is one where even if you delete one edge, all the cycles will be destroyed.
Yes.
Right. So this is with respect to this definition of the matroid. In general, whatever is the definition of independence, minimal dependent subset means the subset C of the universe such that even if you delete one element from C, this independence property, whatever is the way it is defined, will become true. Okay.
Yes.
So let's try the first one, at least the first one.
Can you slightly scroll it up so that I can see the question? Yeah, thanks. So now they are asking, every subset of a circuit is a circuit. Okay.
So circuit is a cycle. Okay. So if see, so circuit is the is a generic term, but if you look at from the perspective of this definition, in in this case, the definition of independence is acyclicity. And when you don't have independence, when you have dependence, that means you have a cycle.
Okay, circuit is a different term.
Now, circuit is the term when you are talking in terms of any matroid. It's a general term. But if you're talking about the matroid that we have seen so far, this matroid in the first question, not first question here. So this matroid which we have seen. With respect to this matroid, when F is a set of H sets of G which are acyclic and is all the set all the edges. The universe is all the edges, and F is subsets of edges which are acyclic. With respect to this matroid, circuit is a cycle. Is it understood?
Yes, yes. But then I was talking about this CICUIT. Is this a typo mistake or is this a separate term, different term?
This is circuit. This is not typo.
In part A.
Oh, this is
In part
oh, this is a typo.
Yes, yes. So now their question is that every subset of a circuit is a circuit. So if I take any subset of the minimal dependence set, so if I take a subset of the minimal independence set, uh, then will this be, so if it is a minimal, it means that removal of one edge is going to make it independent. So if I take a subset of it, then uh, either it will become independent already or may not remain as a circuit. So
Yes, it will, even if you remove one element from the circuit. So if you want to get a subset of a circuit, you are removing at least one element. I think it should have been called proper subset. I think proper subset will be a more appropriate thing to say. So from a circuit, if you remove one element, then you get a subset, at least one element. But as soon as you remove that one element, because it's a minimal dependence set, independence is lost. So it is no more a circuit.
yes, so therefore this is false.
Mm.
And no circuit is contained in any other circuit. So circuit is already minimal. So how can we include a minimal inside a minimal? That won't make much sense. So this is also false.
No,
This is true. This is true.
this is true because this is,
Yes.
think it in terms of a cycle. So if you have another cycle, so that means a subset of this cycle of this. So maybe subset means some edges you have removed. How can that be a cycle? So no circuit, if a circuit contains another circuit, then the cycle contains another cycle. So that would be like saying that, okay, this is a cycle and this is a minimum cycle. That means even if you delete one cycle, so by the definition of minimal dependence set, you delete one edge, it becomes acyclic. Then there is no way a subset of a cycle, which is already minimal, can again be a cycle.
Yes.
So a circuit cannot contain another circuit. No circuit is contained in another circuit. This is true.
Yes. And if C1 and C2 are two distinct circuits, so what's the meaning of the
Distinct
distinctness
means
here?
the elements of C1 and C2 are not identical. So C1 is not equal to C2.
Okay. So then if we take the intersection of the C1 and C2, then nothing is common in between
No, no,
them.
no, that is possible. C1 intersection C2 could be non-empty, but it could be possible that C1 is this and C2 is this. There are some elements which are common to C1 and C2, but there is at least one element in here or here, which is
Okay. 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 Okay.
exclusive.
Yes. Yes. So if I take the intersection of C1 and C2, so then either I will get something. So yeah. So if I take the intersection of it, so what this I here is, I stand for what? This I is
So I
uh,
is the independent set of independent sets. So here independence is defined in a general sense. So you can think of I as, so if you consider this example, you can think of I as a set of acyclic edges.
okay. So now if I have two minimal independent sets, so
No,
then is this
two
necessary
minimal
that
distinct. Yes, distinct is also necessary.
yes, two distinct circuitries. So then if I take the intersection, so but something is common in between C1 and C2.
May be common. So if it's, let us say C1 and C2 were totally disjoint. So that means C1 intersection C2 was in fact phi. In that case, this thing will be phi. And phi is, because we have a matroid, is going to be part of I. That is the first matroid. Uh, this thing.
Yes.
What do they call it? Axiom. The first matroid axiom says the empty set is part of the family. So if C1 intersection C2 is phi, then we are done. Then definitely this is true. But say C1 and C2 are overlapping in some cases, So let us say this is C1, some edges, and let us say C2 is, there are some overlaps. Let us say C2 is this, I don't know. Okay. So C1 intersection C2 is what? Only these two edges.
But
This is
then
also,
here C1 is not minimal dependent, so we'll have to draw some edge so to show the
okay,
dependency.
okay, okay. Sorry, this is the wrong diagram. We have to show a cycle. We have to show a single cycle. So this is C1, and let us say this black one is C2. This is fine. So even if you delete one edge, cyclicity will be lost, independence will be established. A cyclicness
Yes.
will be established. A cyclicness is independence in this case. So intersection of C1 and C2 is going to be part of, yeah. So why is that so? Yeah. See, since C1 and C2 are distinct, so there is, so C1 intersection C2 is not equal to C1. At the same time, C1 intersection C2 is also not equal to C2 because C1 and C2 are distinct. So it cannot
Yes.
happen that there is no, so there is at least one element. So like we draw this diagram. This is C1, this is C2. So there is either one element which is exclusive to C1 or there is one element which is exclusive to C2. So C1 intersection C2, this area cannot encompass the whole of C2. One of these things will happen.
Yes.
So now C1 intersection C2 is not C1 or C2. Did I say or? No, no, no. So both of these things will happen. See, C1 is distinct from C2, and because they're minimal, so both of these things will happen. So no circuit is contained in another circuit that we have already proved.
Yes.
So therefore, C1 intersection C2, whatever it is a subset of C1, and it is also a subset of C2. And because C1 and C2 are minimal dependent circuits, so any subset of them is not a circuit. So they are,
Will be an independent.
yes, will be null. So this is true.
So it is true.
Yes, so if C1 and C2 are two distinct circuits and X is one element in C1 intersection C2, then if you remove X from C1 union C2, then that contains some circuit. So let's refer to this diagram only. So this is the setup. The blue one is C1 and the black one is C2. If you remove, so this is the portion which is in C1 intersection C2. So if you remove one of these edges, then cyclicity is still remaining because it is leading to say C1 has a cycle, C2 has a cycle. But if you remove one guy, so cyclicity in either C1 or C2 will be broken, not both of them. So cyclicity will still be there. So it contains some other circuit. From this diagram, it is clear. Maybe we can give a more formal proof. Okay, since C1 and C2 are two distinct circuits, so if you remove one edge, which is part of C1 as well as C2, so and at the same time you remove the cyclicity of both C1 and C2, that leads to what contradiction? Okay, so that is the
If we take x is equal to null, x is equal to 5, and both C1 and C2 are completely independent, so then the union of C1 and so x will be equals to 5, and then C1 union C2 would definitely be a circuit.
yes.
Uh, Now we can think that what if the x is not equals to 5?
No, no, X1 C1 union C2 will not be a circuit. C1 in C2 will contain some other circuit. Circuit means minimal dependent set.
Oh yes, yes,
So the way to look at it is the following. So because C1 and C2 are distinct, so there is at least one edge which is not common to both C1 and C2. Okay. So let us say that this edge is uh, so the case when x is equal to, so the case when C1 intersection C2 is null is already taken care of, because if C1 intersection C2 is null, then C1 union C2 contains either C1 as a circuit or C2 as a circuit. So both of them are contains a circuit is trivially true in this case. If C1 intersection C2 is 5, then there are two disjoint things. Then C1 union C2 contains a circuit is trivially true. Now suppose that the C1 intersection C2 is not 5, then there is some x which is common to C1 intersection C2. So let's say in this diagram, only one edge, at least one edge is common. So let us say the blue thing is C1 and the black thing is C2. So this edge is common. Now, because they are distinct, so there is at least one. So this circuit C2 cannot be coinciding with C1. So there is some set of edges which is forming C2. Now, even if you delete X via this other route, a circuit remains.
yes,
And now inside the circuit, we will be able to find, I mean, inside this cycle dependent set, we'll be able to find one minimal dependent set, which will be the circuit. That is the reason.
yes,
Mark it
yes,
to it.
convincing. Yes, it is convincing.
Okay. So I think we have shot over time. Fine. Sorry
So
for
what about what? Yeah, what about the next class then? When will you? So there is change in the time. Last class.
this. So you said that on Wednesday will be available, but Tuesday will not be available.
Yes, Tuesday. I mean, any day except Tuesday, because Tuesday we have another session for this 6 to 8 for another subject.
Oh, okay, okay, fine, fine, fine. So I will inform the NPTEL team, and then we can decide with what time we'll do it on Wednesday, or shall we do it on Monday? I think today is already Friday. Monday, doing it Monday will be difficult, but tentatively think that we'll do it on Wednesday.
Okay, okay, yes, yes.
Fine. Thank you for joining.
Thank you so very much. Good night.
Okay.
Yeah, bye everyone.